Every second, the Sun converts 600 million tons of hydrogen into roughly 596 million tons of helium. The missing 4 million tons, that small discrepancy between what goes in and what comes out, is converted entirely into energy, according to a formula that almost everyone has heard of but very few people have truly reckoned with. That missing mass, multiplied by the speed of light squared, becomes 386 trillion joules every single second. It is the most efficient energy conversion process known to physics, and it has been running continuously for 4.5 billion years. We have been trying to replicate it in a laboratory for roughly 70 of those years. The question of why that gap exists, why something the universe does effortlessly in every star you can see in the night sky remains so stubbornly out of reach on Earth, turns out to be one of the most instructive stories in the history of science. It touches on quantum mechanics, plasma physics, materials science, geopolitics, and the basic thermodynamics of energy systems. It involves a cast of characters ranging from a Cambridge astronomer who correctly guessed the energy source of stars a decade before anyone understood nuclear physics, to a New Zealand experimentalist who proved fusion could happen between heavy hydrogen nuclei in the 1930s, to the engineers building the largest scientific machine in human history in the south of France right now. And increasingly, it involves a new generation of private companies backed by some of the wealthiest individuals and institutions on Earth, all betting that what governments and academic consortiums have not yet achieved, a combination of new materials, new computational tools, and new reactor designs just might. Understanding why fusion has proven so difficult, and why that might finally be changing, requires starting not with the machines we build, but with the star that inspired them. At the turn of the 20th century, one of the most embarrassing gaps in scientific knowledge was the question of what powered the sun. Not embarrassing because scientists hadn't tried to answer it. They had. Embarrassing because the best available answer was almost comically wrong. The leading theory at the time was gravitational contraction. The idea ran something like this. As a star radiates heat into space, it loses energy, cools slightly, and contracts inward under its own gravity. That contraction converts gravitational potential energy into heat, which sustains the star's luminosity. The mechanism is real. It operates in the formation of stars. And it explains why Jupiter, which is still slowly contracting, radiates more energy to space than it receives from the sun. Jupiter is shrinking by roughly 2 centimeters every year, and the heat released by that process drives the extraordinary storm systems that swirl across its surface, including the Great Red Spot, a storm that has persisted for centuries. But for the sun, gravitational contraction simply does not work. In 1920, the British astrophysicist Arthur Eddington published a paper making this case with characteristic precision. Eddington calculated that contraction could power the sun for, at most, a few tens of millions of years. Geologists had already established from the fossil record and from radiometric dating techniques that life on Earth was hundreds of millions of years old. The sun had to be at least that old too, and probably much older. So either the geological evidence was wrong, which seemed increasingly unlikely, or the contraction theory was wrong. Eddington concluded the latter without hesitation. He wrote that if the contraction hypothesis were proposed as a novel idea in his own time, it would not stand the smallest chance of acceptance. The word he used for its predictive power was hopelessly inadequate. But the dismissal of one theory is only useful if something better takes its place, and Eddington had a candidate. He suspected that stars were places where hydrogen atoms were being assembled into heavier elements, and he suspected this process was the source of the energy. His inspiration came from a series of precise measurements carried out by his colleague Francis Aston, who had used a device called a mass spectrograph to weigh atomic nuclei with extraordinary accuracy. What Aston found was subtle but profound. A helium nucleus, which contains 2 protons and 2 neutrons, is slightly less massive than 4 individual hydrogen nuclei combined. Not much less. The difference is less than 1% of the total mass. But Eddington recognized immediately what that mass deficit meant in the context of Einstein's equation relating mass and energy. If you took 4 hydrogen nuclei and fused them into 1 helium nucleus, the missing mass would not disappear. It would be converted into energy. And because the speed of light is approximately 300,000 kilometers per second, squaring it produces an enormous number. Even a tiny amount of mass, when multiplied by that number, yields a staggering quantity of energy. Eddington calculated that the mass deficit from hydrogen to helium fusion would be more than sufficient to power the sun for billions of years. The physics worked. The only problem was that nobody at the time had any idea how atoms could actually be made to fuse inside a star. In 1920, quantum mechanics was still in its infancy. The detailed theory of how protons behave at subatomic distances had not yet been worked out. Eddington was essentially making a prediction based on thermodynamic reasoning and mass energy equivalence. He was right about the conclusion without yet having access to the mechanism. That mechanism would take another decade to begin to emerge, and when it did, it revealed something unexpected. The fact that the sun fuses hydrogen at all is, in a rigorous physical sense, something that should not happen, at least not according to classical physics. Here is the problem. For two atomic nuclei to fuse, they must approach each other to within roughly 10 to the power of -15 meters, 1 femtometer, approximately the diameter of a proton. At that distance, the strong nuclear force, the force that holds protons and neutrons together within a nucleus, can reach across and bind them. But protons are positively charged, and like charges repel. As two protons approach each other, the electrostatic repulsion between them grows. To overcome this repulsion, called the Coulomb barrier, the protons would need to be moving at velocities far beyond what the temperature at the sun's core can provide. Even at 15 million degrees Celsius, which is the actual temperature at the solar core, protons travel at roughly 500 kilometers per second. The kinetic energy corresponding to that speed is about 1,000 times less than what would classically be required to climb over the Coulomb barrier. Classical physics predicts, therefore, that solar fusion should be essentially impossible. The sun should not be burning, and yet it manifestly is, which means something else is happening. That something else is quantum tunneling. In quantum mechanics, particles do not have perfectly defined positions and trajectories. Instead, they are described by probability waves, spread out distributions of likelihood across space. One consequence of this wave nature is that a particle approaching a barrier does not simply bounce off if its energy is insufficient. Instead, the particle's wave function extends into and through the barrier, which means there is a non-zero probability that the particle will appear on the other side, even without having the classical energy to climb over. This is tunneling, and it is not a quirk or an approximation. It is a direct consequence of quantum mechanics. It operates everywhere in nature at the subatomic scale. It is why radioactive nuclei decay on timescales that classical physics cannot explain. It is why certain chemical reactions proceed at temperatures that classical transition state theory predicts should be insurmountable. In the sun, quantum tunneling allows protons to fuse despite having nowhere near the classical energy required. But the probability of tunneling through the Coulomb barrier at any given proton-proton encounter is extraordinarily small. In roughly 10 to the power of 28 proton-proton interactions, quantum tunneling succeeds, and the protons get close enough for the strong force to take over. The number 10 to the 28th is so large it defies easy comprehension. It is roughly 10 billion times larger than the number of atoms in the observable universe. The sun gets away with such an improbable process only because it contains an almost unimaginable number of protons and an almost unimaginable volume of plasma in which they are constantly colliding. But tunneling through the Coulomb barrier is only the first obstacle. Once two protons are brought together by the strong force, they form a nucleus of helium-2, a diproton containing two protons and no neutrons. This nucleus is extraordinarily unstable. It decays almost immediately back into two separate protons. For the fusion reaction to progress, one of those protons must undergo a transformation called beta decay, converting into a neutron. This process is mediated by the weak nuclear force. And the weak force is, as its name implies, weak, not in the everyday sense, but in the specific quantum mechanical sense that the particles mediating it, the W bosons, are extremely massive, which makes the force short-ranged and the reactions it governs extremely slow. The combination of the rare quantum tunneling event and the slow weak force beta decay means that a typical proton in the sun's core waits, on average, approximately 10 billion years before it undergoes fusion. 10 billion years, roughly the current age of the universe, is how long a single proton has to wait its turn. The sun has existed for 4.5 billion years, and it will exist for roughly another 5 billion before it exhausts its fuel. This slow burn is not a design flaw. It is, from our perspective, the most fortuitous physical constraint imaginable. If the proton-proton reaction were faster, if weak force beta decay happened more readily, the sun would have burned through its hydrogen in a cosmological instant, and we would not be here to observe it. So the sun fuses protons through a process that is statistically almost impossible, sustained only by the sheer scale of the number of particles involved. What does this mean for engineers trying to recreate fusion on Earth? It means simply that proton-proton fusion on Earth is out of the question. The probabilities are so low, and the volumes of plasma achievable in any laboratory device so small compared to the sun, that the expected reaction rate approaches zero in any practical engineering sense. The proton-proton chain has never been directly measured in a laboratory because it would take longer than the age of the universe to observe a meaningful number of events in any device we could build. Fusion researchers have known this since the mid-20th century, and so rather than replicating what the sun actually does, they have focused on identifying combinations of nuclei that are far more reactive, combinations that do not require the weak force, and that have lower Coulomb barriers. The most important of these combinations, the one that drives almost all fusion research today, was first put to use in weapons rather than power plants. It is the reaction between deuterium and tritium, the two heavy isotopes of hydrogen. Ordinary hydrogen contains one proton and no neutrons in its nucleus. Deuterium contains one proton and one neutron. Tritium contains one proton and two neutrons. Both are hydrogen isotopes. They behave chemically like hydrogen, forming water and other hydrogen compounds, but their nuclei are heavier and, crucially, far more reactive with each other than ordinary protons. The reason comes down to the Coulomb barrier and the strong force. Because deuterium and tritium already have neutrons, the reaction between them does not require the weak force to convert a proton into a neutron. The rate-limiting step of the proton-proton chain is simply absent. Deuterium-tritium fusion proceeds at a rate roughly 24 orders of magnitude, a million billion billion times faster than proton-proton fusion at the same temperature. This is the reaction that first achieved fusion in the hydrogen bomb in the early 1950s. The explosive force of those early thermonuclear weapons came from deuterium-tritium fusion, triggered by a fission bomb detonation. The energy yield was extraordinary, and it demonstrated beyond any doubt that deuterium-tritium fusion was physically achievable. The challenge, for power generation, was to achieve it in a controlled and sustained way, rather than in a microsecond catastrophic explosion. The deuterium-tritium reaction produces two products: an alpha particle, a helium-4 nucleus containing two protons and two neutrons, and a free neutron. The energy is divided between them. Roughly 80% is carried away by the neutron, and 20% by the alpha particle. Understanding the implications of this energy distribution is essential to understanding why fusion power generation is so difficult. The alpha particle, being electrically charged, is contained within the plasma by the same magnetic or inertial forces that confine the rest of the plasma. Its 20% share of the fusion energy goes directly back into heating the plasma, which helps sustain the reaction. This is what physicists call alpha heating, and it is a crucial part of achieving a self-sustaining fusion plasma. The neutron, however, is electrically neutral. Magnetic fields do not affect it. It shoots straight out of the plasma at roughly 1/6 the speed of light, about 50,000 kilometers per second, in whatever direction it was produced, caring nothing for the careful engineering surrounding it. Capturing that neutron and extracting its energy is the central engineering problem of fusion power. Most reactor designs address this with what is called a blanket, a layer of material surrounding the reaction chamber, thick enough to absorb the high-energy neutrons and convert their kinetic energy into heat. That heat is then used to generate steam, drive a turbine, and produce electricity. The principle is straightforward. The implementation is extremely difficult. The difficulty has two aspects. First, the neutrons do not simply stop in the blanket and politely deposit their energy. They scatter off nuclei in the blanket material, and at each scatter they may induce nuclear reactions that transmute the blanket material into different elements, some of which are radioactive. Over time, this neutron bombardment changes the physical properties of the materials it passes through. Metals become brittle, welds weaken, radiation-sensitive electronics malfunction. The walls of a fusion reactor must absorb a neutron flux that is, in some designs, comparable to the environment inside a fission reactor. Components must be replaced on timescales that affect the economics of the plant. The search for materials that can withstand decades of neutron bombardment without degrading is an active and extremely challenging field of materials science. Second, the blanket must be designed to breed tritium. And this brings us to the most overlooked supply problem in fusion energy, the tritium problem. Tritium does not occur in any meaningful quantity in nature. Unlike deuterium, which can be extracted from ordinary seawater, heavy water makes up roughly 1 in every 6,400 water molecules. Tritium is essentially absent from the natural environment. It has a radioactive half-life of 12.3 years, which means any tritium that was present at the formation of the solar system has long since decayed into helium-3. The only sources of tritium on Earth today are human-made. Most of it comes as a byproduct of Canada's CANDU reactors, pressurized heavy water reactors that produce tritium as a neutron absorption product. Each of Canada's 19 deuterium-uranium reactors produces roughly 0.5 kilogram of tritium per year. Global tritium reserves currently stand at approximately 25 kilograms. A commercial fusion power plant, according to estimates from ITER, the International Thermonuclear Experimental Reactor under construction in southern France, would require roughly 125 kilograms of tritium per year to operate. The global reserve would run out in weeks. Moreover, Canada is in the process of decommissioning several of its CANDU reactors over the coming decade, meaning even that meager supply is set to decline. The tritium problem is not a distant concern for a mature fusion industry. It is a constraint that must be solved before the first commercial plant can operate. The intended solution is tritium breeding within the reactor itself. Lithium, when struck by a neutron, undergoes a reaction that produces helium and tritium. If the reactor blanket is made of lithium, or a lithium compound, the same neutrons that cause material damage might also generate fresh tritium fuel. In principle, each fusion reaction produces one neutron, which breeds one tritium atom, which fuels one future fusion reaction. A perfect cycle. In practice, the efficiency of neutron capture and tritium production is never 100%. Some neutrons escape. Some are absorbed by structural materials without producing tritium. Some induce reactions that produce helium gas, which accumulates within the blanket material and causes it to swell and degrade, a phenomenon called helium embrittlement. Running the numbers reveals that a reactor operating at realistic efficiencies would consume tritium faster than it breeds it, with the supply steadily diminishing over time. The proposed engineering solution is to add materials that act as neutron multipliers, substances that absorb one incoming neutron and release 2 or more. Beryllium and lead are the primary candidates. Beryllium in particular is attractive because it has a high neutron multiplication rate, but beryllium is toxic, which complicates handling and disposal. It also contains trace amounts of uranium, and when uranium absorbs neutrons, it produces radioactive transuranic elements, undermining one of fusion's supposed advantages over fission. Lead is less toxic but denser and heavier, affecting reactor design. There is no clean solution to the tritium breeding problem, only a series of engineering compromises, each of which introduces new challenges. Set this aside and consider the plasma confinement challenge, which predates the tritium problem and remains central to all fusion research. The plasma required for deuterium-tritium fusion on Earth must reach temperatures of roughly 150 million degrees Celsius, 10 times hotter than the core of the Sun. The reason such extreme temperatures are required is that we cannot replicate the Sun's other great advantage, pressure. At the solar core, the pressure is approximately 340 billion times atmospheric pressure, and the plasma density reaches 150 grams per cubic centimeter, denser than gold. The mass of the entire Sun, about 2 times 10 to the power of 30 kilograms, is pressing down from above, forcing protons into proximity with each other continuously. In a laboratory fusion device, the plasma mass is measured in grams rather than sextillions of kilograms. ITER, the largest tokamak ever built, will contain approximately 1 gram of plasma in a reaction chamber of 830 cubic meters. That extraordinary disparity in density means that the plasma must compensate with temperature. Particles must be moving fast enough that even their brief, low-probability encounters generate fusion events in sufficient numbers to produce usable energy. 150 million degrees Celsius is not a temperature that any material can physically contain. The plasma cannot touch the walls of the reactor. Any contact would instantly cool the plasma below fusion temperatures and cause severe damage to the wall. The plasma must therefore be confined without touching anything. Two fundamentally different approaches to this problem have been developed. The first is magnetic confinement fusion. Plasma is a mixture of positively charged ions and negatively charged electrons, a soup of charged particles. Magnetic fields exert forces on charged particles, constraining their trajectories. A carefully designed magnetic field configuration can make charged particles spiral along field lines in ways that keep them away from physical surfaces. The dominant design is the tokamak, a Russian acronym from the 1950s, meaning toroidal chamber with magnetic coils. In a tokamak, a strong toroidal magnetic field wraps around a donut-shaped vacuum chamber, and a second poloidal field induced by a current flowing through the plasma itself combines with the toroidal field to create a helical magnetic structure that keeps the plasma confined in a twisted ring. Tokamaks have been the main focus of government-funded fusion research. Since the 1960s, the experimental results from tokamaks have been consistently encouraging. Plasma temperatures, densities, and confinement times have all improved over the decades. But the physics of plasma instabilities has meant that large amounts of energy are required to maintain the magnetic fields and to heat the plasma, and ensuring that energy output exceeds energy input has proven extremely difficult. The second approach is inertial confinement fusion, which draws its inspiration from thermonuclear weapons. A small pellet of deuterium-tritium fuel, typically a hollow sphere a few millimeters in diameter, is hit simultaneously from many directions by intense laser beams or energetic particle beams. The outer layer of the pellet ablates explosively, driving a shockwave inward that compresses and heats the fuel to fusion conditions for a few nanoseconds. During those nanoseconds, fusion occurs, energy is released, and the plasma disperses before it can cause damage. The cycle then repeats at high frequency. The advantage of inertial confinement is that there are no magnets to maintain and no continuously sustained plasma to manage. Each fuel pellet is an independent event. The disadvantage is that the energy required to fire the lasers or accelerators is enormous, and the efficiency of laser systems, the fraction of wall plug electricity that ends up as coherent light on target, has historically been very low. The lasers must deliver precisely shaped pulses with extraordinary timing, precision across all beams simultaneously. The symmetry of the compression must be near perfect to achieve the required densities, because any asymmetry will cause the plasma to jet outward unevenly, reducing compression and preventing ignition. In December of 2022, the National Ignition Facility at Lawrence Livermore National Laboratory in California achieved something that had eluded fusion researchers for decades. Using 192 laser beams delivering 2.05 megajoules of ultraviolet light to a tiny deuterium-tritium capsule, the facility obtained 3.15 megajoules of fusion energy out. This was the first time in history that a fusion reaction had produced more energy than the laser energy delivered to the target, what physicists call ignition in the technical sense of the term. The scientific community responded with justified celebration. It was a genuine and significant milestone. However, the context matters enormously. The 2.05 megajoules delivered to the target required approximately 300 megajoules of electrical energy to generate in the facility's laser systems an energy conversion efficiency of less than 1%. The net energy balance, accounting for total electrical input rather than just laser energy on target, was deeply negative. The fusion yield exceeded the laser input, but it was swamped by the electricity consumed. For the National Ignition Facility result to represent a path to commercial power, laser efficiency would need to improve by a factor of somewhere between 50 and 100, which would take the technology well beyond anything demonstrated in any laser system to date. None of this diminishes the physics achievement. Ignition in the technical sense, more fusion energy out than laser energy in, is real and important, but it is distant from net energy gain in the engineering sense, which is what actually matters for a power plant. The experimental jet reactor in the United Kingdom, a tokamak operated jointly by the European Union member states and the UK, achieved its own record in late 2023. It produced 69 megajoules of fusion energy from just 0.2 milligrams of deuterium-tritium fuel over a sustained pulse of approximately 5 seconds. This shattered JET's previous world record and confirmed that the physics understanding of plasma confinement and alpha heating was on solid ground. JET was subsequently decommissioned after this result, a planned shut down after decades of operation, having generated enormously valuable data that will inform the design of future devices. The most ambitious government-funded fusion project in history is ITER, situated at Cadarache in southern France. ITER is an international collaboration involving 35 nations, including the European Union, the United States, China, Russia, India, Japan, and South Korea. It is designed to produce 500 megawatts of fusion power from 50 megawatts of heating input, a fusion gain factor, commonly denoted Q, of 10. This would be the first demonstration that fusion can produce substantially more energy than it consumes in operation. ITER is not designed to generate electricity. It has no turbines, no generators. It is a scientific experiment designed to prove that sustained high-gain fusion is physically achievable in a tokamak at reactor-relevant scale. Construction of ITER has been ongoing for years and has involved extraordinary logistical and engineering challenges. The superconducting magnets that will confine the plasma must operate at -269 degrees Celsius, colder than outer space, while the plasma a meter away is at 150 million degrees. The temperature gradient across a few meters of reactor hardware is the largest sustained temperature differential in any human-made structure. Individual magnet components weighing hundreds of tons have been manufactured on multiple continents and shipped to France for assembly. The vacuum vessel alone, the inner chamber that contains the plasma, consists of 9 sectors, each weighing over 400 tons. That must be assembled to tolerances of less than 2 millimeters. ITER's current timeline has it achieving first plasma around the mid-2030s, with full deuterium-tritium experiments following several years later. The project has faced delays and cost overruns, as virtually all projects of comparable complexity do. But the underlying physics has not changed, and there is broad consensus in the plasma physics community that ITER, when operational, will achieve its scientific goals. While ITER inches forward, a different dynamic has emerged in the fusion landscape. Private capital has poured into the sector at a rate that would have been unimaginable a decade ago. The reasons are partly technological. New high-temperature superconductors have become available that can generate much stronger magnetic fields in smaller packages, and partly cultural, as the success of private space companies in fields previously dominated by government programs has encouraged entrepreneurs to look at other areas where private investment might move faster than public institutions. Commonwealth Fusion Systems, based in Cambridge, Massachusetts, emerged from MIT's Plasma Science and Fusion Center. The company's central bet is on high-temperature superconducting magnets made from a material called rare earth barium copper oxide, commonly abbreviated REBCO. These magnets can generate fields of roughly 20 Tesla, approximately twice the field strength achievable with conventional superconducting magnets at similar scale. Because the plasma confinement properties of a tokamak scale vary favorably with magnetic field strength, specifically, the fusion power scales roughly as the fourth power of the field. A doubling of field strength means the same confinement quality can be achieved in a device with roughly 1/16 the volume. A smaller device is dramatically cheaper and faster to build, maintain, and iterate on. In September of 2021, Commonwealth Fusion Systems demonstrated that its high-temperature superconducting magnet technology worked, achieving a field of 20 Tesla in a large-bore research magnet. At the time, the strongest sustained field of its kind ever produced. The company is now building its demonstration device, called Spark, at a facility in Devons, Massachusetts. Spark is designed to achieve Q greater than 2, fusion gain greater than 2, meaning more than twice as much fusion energy out as heating energy in, making it the first tokamak to demonstrate net energy gain in the engineering sense. If Spark succeeds, Commonwealth Fusion Systems plans to build a commercial plant called ARC. The company has secured backing from Google, Nvidia, Bill Gates' Breakthrough Energy Ventures, and numerous other investors. It claims it will have a commercial plant online in the early 2030s. Helion Energy, based in Everett, Washington, takes a fundamentally different approach. Rather than a conventional tokamak, Helion has developed what it calls a field reverse configuration, a type of magnetic confinement in which the plasma itself carries currents that generate its own magnetic field, holding the plasma in a compact, elongated blob without a central coil threading through the plasma volume. Helion's device, called Polaris, fires 2 of these plasma rings at each other from opposite ends of a linear chamber at speeds exceeding 1 million kilometers per hour. When the two rings collide and compress, the plasma briefly reaches fusion conditions. More unusual still is Helion's choice of fuel. Rather than deuterium and tritium, Helion proposes to use deuterium and helium-3. The deuterium-helium-3 reaction produces an alpha particle and a proton, both electrically charged, rather than an alpha particle and a neutron. This is significant for two reasons. First, the absence of a high-energy neutron means there is essentially no neutron damage to reactor components and no need for tritium breeding. Second, because the reaction products are charged, their energy is retained within the plasma, where it can drive an increase in magnetic pressure. Helion's design proposes to capture this energy directly through electromagnetic induction rather than by heating water to drive a steam turbine, a potentially more efficient conversion path that eliminates many of the engineering complexities of a conventional thermal power cycle. The catch, and there is always a catch in fusion, is that helium-3 is even rarer than tritium. It is essentially absent from Earth's surface. The only terrestrial source is the decay of tritium, which produces helium-3 as its daughter product. To get around this, Helion proposes to operate a separate class of reactors running on deuterium-deuterium fuel, specifically to breed helium-3 for use in its primary commercial plants. Deuterium-deuterium fusion does produce helium-3, but it also produces tritium and, in one of its branches, energetic neutrons, reintroducing the neutron damage problem for the breeder reactors, even if the commercial plants avoid it. The deuterium-helium-3 reaction also requires higher temperatures and plasma densities than deuterium-tritium fusion, adding to the engineering challenge. Helion has signed an agreement with Microsoft to begin supplying electricity from its first commercial plant by 2028, with financial penalties if it fails to do so. Whether that timeline is achievable is debated within the fusion community. What is not debated is that Helion's approach is technically coherent and represents a genuine alternative to the mainstream tokamak program. TAE Technologies, formerly Tri-Alpha Energy, has been working since 1998 on an even more distant fusion goal, the proton-boron reaction. Boron-11, when struck by a proton, fuses to produce 3 alpha particles and no neutrons at all, a completely aneutronic fusion reaction. This would eliminate neutron damage entirely, and both fuel components are abundant and cheap. The catch is that proton-boron fusion requires plasma temperatures roughly 10 times higher than deuterium-tritium fusion, in the range of 1 to 3 billion degrees Celsius, and, even at those temperatures, the reaction cross-section is far smaller than deuterium-tritium. TAE has raised over $1 billion and has demonstrated plasmas at temperatures exceeding 75 million degrees Celsius in its Norman device, but it has not yet demonstrated proton-boron ignition. The company believes that machine learning techniques applied to plasma control will allow it to achieve the required plasma conditions. The involvement of artificial intelligence and machine learning in fusion research is a genuine and recent development, not merely a marketing angle. Plasma instabilities in tokamaks develop on timescales of milliseconds or less, far faster than human operators can respond. In 2022, researchers at DeepMind, in collaboration with the Swiss Plasma Center at EPFL, demonstrated that a reinforcement learning algorithm could control the magnetic field configuration of a tokamak in real time, maintaining and even sculpting novel plasma shapes that human operators had not previously attempted. The algorithm learned control strategies entirely from interaction with a simulation, then transferred those strategies directly to the real device. This kind of adaptive real-time control is genuinely new, and it addresses one of the most persistent challenges in plasma confinement: keeping the plasma stable against the many instabilities, kink modes, ballooning modes, disruptions that can abruptly terminate a plasma discharge and, at high power, damage reactor components. Beyond control, machine learning is being applied to the design of reactor components, the prediction of material degradation under neutron bombardment, and the analysis of experimental data from running plasmas. The volume of data produced by a large tokamak discharge is enormous. Thousands of diagnostic channels sampled millions of times per second, and extracting the relevant information from that data in near real time is a task well suited to modern neural network architectures. The cumulative effect of these tools is not to solve the physics problems of fusion, but to accelerate the experimental iteration cycle to learn faster from each experiment what the plasma is doing and why, which in turn suggests more effective approaches for the next experiment. The fuel picture for fusion, looked at honestly, reveals some important caveats to the commonly repeated narrative that fusion power will use an essentially unlimited supply of hydrogen from seawater. Deuterium, the heavier isotope of hydrogen present in seawater at a ratio of about 1 in 6,400, is genuinely abundant. The world's oceans contain roughly 45 quadrillion tons of water, from which deuterium could be extracted in quantities sufficient to supply civilization's energy needs for billions of years. That part of the narrative is accurate. Lithium, needed for tritium breeding in deuterium-tritium reactors, is another matter. Lithium is used in the blanket to absorb neutrons and produce tritium. Lithium is also used in lithium-ion batteries, the demand for which is growing rapidly with the electrification of transportation and energy storage. Whether lithium supplies are sufficient to support both industries at scale, and for how long, is a live question. Global lithium reserves are estimated at somewhere between 20 and 80 million tons. Estimates vary widely because lithium exploration has intensified in recent years with rising demand. A mature global fusion industry running on deuterium-tritium would require lithium at rates that some analysts suggest could strain supply over a century-long timescale, though this depends heavily on assumptions about reactor efficiency, breeding ratios, and the rate of fusion deployment. Energy gain is the parameter that matters most for assessing the viability of any fusion approach, and the terminology around it is unfortunately confusing. Physicists typically discuss fusion gain using the letter Q, defined as the ratio of fusion energy produced to the energy used to heat the plasma. By this definition, a Q of 1 means the plasma produces as much fusion energy as was used to heat it, break even in the physics sense. But a commercial power plant must also account for the energy used to generate and maintain the magnetic fields, operate the cooling systems, run the plasma diagnostics and control systems, and heat the fuel before it enters the plasma. The engineering Q, fusion energy outdivided by total electrical energy consumed by the plant, must be substantially greater than 1 before any useful electricity can reach the grid. ITER aims for a Q of 10 in the plasma physics sense, which would be a major scientific achievement. But even at Q equal to 10, accounting for the efficiency of converting fusion energy to electricity and the parasitic power loads of the facility, the net electrical output would be modest and the economic case far from obvious. The demonstration devices currently under construction, ITER, Spark, Helion's Polaris, are steps toward commercial viability, not demonstrations of it. The engineering challenges between a successful Q equals 10 experiment and a commercially competitive power plant are substantial, and they should not be minimized. At the same time, the trajectory of fusion research has clearly shifted. For most of the history of controlled fusion research, progress was linear, a slow accumulation of improved plasma parameters in successively larger and more expensive devices, funded almost entirely by national governments on decade-long timescales. The entry of private capital, the availability of new superconducting materials, and the application of computational tools including machine learning have introduced a faster iteration cycle and a diversity of approaches that simply did not exist before. Different reactor concepts, tokamaks with conventional magnets, tokamaks with high-temperature superconductors, field-reversed configurations, inertial confinement, are all being pursued simultaneously, each embodying different assumptions about where the cost and performance leverage lies. This diversity matters. In the history of technology development, the approach that ultimately succeeds commercially is frequently not the one with the best early laboratory results, but the one that combines adequate physics performance with superior engineering economics. It is not clear today which fusion concept will prove most commercially competitive. What is clear is that the range of serious contenders is wider than it has ever been. The geopolitical dimension of fusion energy also deserves attention. ITER is a collaboration spanning adversarial powers. The United States and Russia, China and Japan, India and the European Union all contribute components, expertise, and funding. The cooperation is not always smooth. Political tensions between member nations have at times complicated procurement, financing, and information sharing. But the project has continued, which is itself remarkable. The scientific communities of nations that are strategic competitors have found in fusion research a domain where collaboration is sufficiently valuable to both sides that it persists through political friction. Whether this model will extend to a future mature fusion industry, or whether fusion power will become a strategic national asset that nations attempt to monopolize, is an open question with significant implications for how its benefits are distributed globally. Climate change gives fusion an urgency that it did not have in the 1950s and 60s, when the first fusion experiments were conducted. At that time, the motivation was primarily the promise of unlimited energy in a world of abundant fossil fuels, an insurance policy against eventual resource depletion. Today, the decarbonization of the global energy system is an acute and time-sensitive requirement, and fusion is being evaluated not just on its ultimate potential, but on how quickly it can contribute. This temporal pressure is both an advantage and a risk for fusion advocates. It attracts investment and political attention. It also creates incentives to make optimistic timeline claims that, if not met, erode public credibility. The history of fusion is littered with predictions that have not been borne out. The cliché that fusion power is always 30 years away has been applied consistently since the 1950s, and the fact that commercial fusion power is not yet available suggests that the cliché, frustrating as it is, contains a grain of truth, not about fusion's theoretical limits, which have never been seriously in question, but about the pace at which engineering challenges can be overcome in a technology this complex. What Arthur Eddington wrote in 1920, before quantum mechanics, before the strong nuclear force, before nuclear reactors of any kind existed, was a prediction based on a deduction. He reasoned from the mass-energy equivalence and Aston's atomic mass measurements to the conclusion that stars must be running on subatomic energy, nuclear energy, and that if this energy could be tapped by human civilization, the supply would be effectively inexhaustible. The store, he wrote, is well-nigh inexhaustible, if only it could be tapped. A century later, we know he was right about the physics in every particular. Stars are nuclear fusion reactors. The energy density of fusion fuel is approximately 10 million times greater than that of chemical fuels like coal or natural gas. 1 gram of deuterium-tritium fuel contains roughly the energy equivalent of 2,400 gallons of oil. The fuel is abundant. The reaction products are, compared to fission, relatively benign. There is no long-lived radioactive waste in the sense of spent nuclear fuel rods that must be sequestered for tens of thousands of years. The activated reactor components that result from neutron bombardment are radioactive, but on timescales of decades to a century rather than millennia, and with careful material selection, this radioactive inventory can be significantly reduced. Question Eddington could not answer, and that remains open, is whether the engineering challenges of controlled fusion on Earth can be solved at a cost that makes fusion power economically competitive with other energy sources. The comparison set is different from what it was even a decade ago. Solar photovoltaics and wind power have fallen in cost by a factor of 10 or more over the past 15 years. Battery storage costs are declining. The economic target that fusion must hit to be commercially relevant is a moving one, and it is moving in the wrong direction from fusion's perspective. Fusion does not need merely to work. It needs to work at a cost per unit of electricity competitive with renewable generation plus storage, which is already quite cheap and getting cheaper. This does not mean fusion is irrelevant. There are aspects of energy supply that variable renewables struggle to address. Deep industrial heat, long-duration energy storage, firm dispatchable generation for grids with high renewable penetration, and energy supply in geographic regions with poor solar and wind resources. Fusion, if it can be made to work economically, addresses all of these. A compact fusion reactor that can be deployed anywhere, run on fuel extracted from seawater, and produce firm power on demand would be genuinely valuable, even in an energy system that is already substantially electrified by renewables. The physics of fusion is settled. The sun demonstrates it every second of every day. What the next decade of experimentation, from ITER's first operations, to Spark's planned demonstration of net energy gain, to Helion's first commercial attempts, to whatever results emerge from the dozens of smaller private ventures working on alternative concepts, will determine is whether the engineering of fusion is tractable on a commercially relevant timescale. That question has not yet been answered. The experiments currently underway will begin to provide answers within this decade. The fact that we are still asking the question, after 70 years of determined effort, is not evidence that fusion is impossible. It is evidence of how difficult the engineering is. The sun does fusion easily. We do not have the sun's mass. We do not have the sun's gravity. We do not have the sun's patience, burning for billions of years through an astronomically vast reservoir of hydrogen. What we have instead are the tools of quantum mechanics, superconducting materials, laser technology, plasma diagnostics, computational simulation, and machine learning. And we have the knowledge that the physics works, that deuterium and tritium, brought together at sufficient temperature and pressure, will fuse, will release energy in quantities that dwarf any chemical reaction, and will do so cleanly and in a way that can, in principle, be sustained. What we do not yet know is exactly when that principle will find a practical form. But for the first time in the history of fusion research, the people working on the problem are optimistic in a way that is backed by specific technical milestones rather than general aspiration. The December 2022 result from the National Ignition Facility was not a path to commercial power by itself, but it was proof that ignition, fusion plasma producing more energy than was used to initiate it, is physically achievable in a laboratory device. The jet record of 69 megajoules from a tokamak plasma in late 2023 confirmed that deuterium-tritium fusion in magnetic confinement can produce fusion energy at scale. ITER's construction continues. Sparker's high-temperature superconducting magnets have been demonstrated. Private investment in the sector reached an estimated $6 billion in 2023, with more commitments announced regularly. The barriers that remain are real. Tritium breeding must be demonstrated at scale. Neutron-resistant materials must be developed and validated over operational lifetimes. Plasma control in burning plasmas, where the fusion energy itself is the dominant heating source, has not yet been demonstrated in any device and will present new physics challenges. The economics of building, maintaining, and fueling a fusion plant must be worked out in detail, and those economics will likely be the decisive factor in whether fusion plays a major role in the energy transition or remains a technology of great promise that arrived too late and too expensively to compete. None of these barriers is obviously insurmountable. Each has a plausible engineering path. What remains is the hard, expensive, time-consuming work of walking those paths, running experiments, failing, learning, redesigning, and running the next experiment. This is how all of engineering works at the frontier. It is slow, it is expensive, and it is the only way anyone has ever figured out how to do it. Eddington's guess, a century ago, was that the energy powering the stars was available in principle to human civilization. A century of physics and engineering has confirmed the first part of that guess and is still working out the second. The reservoir is inexhaustible. The tap is proving difficult to engineer, but the tools available to the engineers working on the tap today are better than at any point in the history of the effort. Whether that is enough, and whether it is enough in time to matter for the energy challenges of the 21st century, are questions whose answers are now being written in plasma, chambers in France and Massachusetts and Washington, and the United Kingdom and China, and South Korea and a dozen other places where physicists and engineers are doing the painstaking work of turning a star's secret into a power source for a civilization that urgently needs one. If this kind of deep dive into the science shaping our future is something you want more of, hitting like and subscribing costs you nothing and makes a genuine difference to whether content like this continues to be made. The research continues. The physics does not change. The engineering gets better, and somewhere inside every tokamak discharge, every laser-driven implosion, every field-reversed configuration firing its plasma rings together at 1,000,000 kilometers per hour, the same process is occurring. The same process that has powered the sun for 4.5 billion years, and every other star in the galaxy, for as long as there have been stars. We are not yet masters of that process, but we understand it, we can demonstrate it, and we are getting measurably better at sustaining it. The question is no longer whether fusion works. The question is whether we can make it work for us, on our time scale, at our scale, and at a cost we can afford. That is an engineering question, not a physics question. And engineering questions, given enough time and effort and ingenuity, tend eventually to get answered. The plasma physics underpinning fusion research has grown into one of the most sophisticated branches of applied physics in existence. The behavior of a hot, dense plasma threaded by magnetic fields is governed by equations that couple fluid dynamics, electromagnetic theory, and kinetic theory into a system of such mathematical complexity that even the most powerful supercomputers available today can only simulate it accurately for fractions of a second of real plasma behavior. Understanding and predicting how plasmas behave in the boundary regions, near the reactor wall, where the temperature drops from hundreds of millions of degrees to near room temperature over a distance of a few centimeters, remains an active area of theoretical and experimental research. The edge of a fusion plasma is particularly challenging because it is the region where the plasma interacts, however briefly, with solid material. In a tokamak, the plasma edge is managed by a component called the diverter, a specially designed structure that channels the exhaust from the main plasma, including energetic ions and neutral particles, away from the plasma-facing walls and into a cooler exhaust region. The diverter must absorb enormous heat loads, potentially tens of megawatts per square meter in a reactor-scale device. For comparison, the heat flux on the surface of the space shuttle during re-entry from orbit was roughly a few megawatts per square meter. The diverter surfaces in a fusion reactor must survive heat loads potentially 10 times greater. Continuously for years, tungsten is currently the leading material for plasma-facing components in tokamaks because of its extremely high melting point of 3,422 degrees Celsius, higher than any other pure element. But tungsten has its own problems. It is brittle at room temperature and becomes more so under neutron irradiation. If a plasma disruption occurs and the plasma suddenly loses confinement and contacts the wall, the resulting heat pulse can melt tungsten surfaces and deposit tungsten vapor into the plasma, quenching the fusion reaction and potentially requiring complex cleanup before the reactor can restart. Managing disruptions, preventing them where possible, mitigating their effects when they occur, is one of the most technically demanding aspects of tokamak operation. The concept of a disruption illustrates something important about the practical gap between fusion physics experiments and a commercial power plant. In a research device like JET or the tokamaks in operation today, disruptions are a known risk, but a manageable one. The device is designed for research. The plasma current is lower than a reactor, and the consequences are less severe. In a commercial power plant, disruptions would need to be either prevented entirely through advanced control systems, or reduced in severity through disruption mitigation systems that inject material into the plasma when a disruption is detected, distributing the energy more broadly rather than allowing it to concentrate in a small area of the wall. Designing such systems, demonstrating their effectiveness in reactor conditions, and qualifying them for long operational lifetimes is a substantial engineering program in its own right. The EE neutron flux that a commercial fusion reactor would expose its components to is quantified in units of displacements per atom, a measure of how many times each atom in the structural material is knocked out of its lattice position by neutron impacts. A commercial fusion reactor running at high power would expose its first wall and blanket components to flux levels that would cause tens to hundreds of displacements per atom over their operational lifetime. Understanding how structural materials, steels, ceramics, composites, behave after such extreme radiation exposure requires either testing them in fission reactors that can approximate the neutron flux, or building dedicated fusion neutron irradiation facilities. The International Fusion Materials Irradiation Facility planned to produce a 14 megaelectron-volt neutron beam comparable to a fusion neutron source, has been discussed for decades but not yet built. Without such a facility, materials qualification for fusion conditions relies on fission neutron testing and extrapolation, an approach that introduces significant uncertainty into reactor design. This is not a fundamental obstacle, but it is a genuine gap in the experimental foundation of fusion engineering, and addressing it will require dedicated international investment. The socio-technical dimensions of fusion deployment also deserve consideration. Energy infrastructure is not deployed in a physical and economic vacuum. A fusion power plant, if one is built in the late 2020-30s or 2042nd, will enter energy markets that have already undergone substantial transformation. In many countries, the share of electricity from variable renewables, solar and wind, is projected to reach 50 to 80% within the next 2 decades. Grid systems built around high renewable penetration have very different economics and operational characteristics than those built around dispatchable generation. Fusion, if it produces firm, controllable power, is well suited to complement renewable generation by providing the baseload and dispatchable capacity that maintains grid stability when solar and wind output is low. but demonstrating that fusion plants can be operated flexibly, cycling power output, up and down in response to grid needs, is an additional engineering requirement beyond simply achieving net energy gain. The regulatory framework for fusion power plants is also underdeveloped. Fusion does not produce a chain reaction that can run away. You cannot have a Chernobyl or a Fukushima with a fusion reactor. If the plasma loses confinement, the reaction simply stops within seconds, because there is never more than a few grams of fuel in the plasma at any time. The radiological inventory of a fusion plant, primarily in the form of tritium and activated structural materials, is substantially smaller and shorter-lived than that of a fission plant. But fusion is still a new technology, and regulatory agencies in most countries have not yet developed the frameworks, standards, and licensing pathways that would allow a fusion plant to be built and operated commercially. In the United States, the Nuclear Regulatory Commission in 2023 issued a final rule establishing a regulatory framework for commercial fusion energy systems, distinct from the framework applied to fission reactors. This was an important step, recognizing that fusion's risk profile is sufficiently different from fission that applying fission regulations wholesale would be inappropriate, either overly restrictive in ways that would unnecessarily impede fusion development, or mismatched with the actual risks in ways that would create regulatory blind spots. Similar regulatory frameworks are being developed in the United Kingdom and European Union. This work is unglamorous compared to the physics breakthroughs that attract headlines, but it is essential infrastructure for a functioning fusion industry. Public understanding of fusion is shaped largely by contrast with fission. When people hear nuclear, they often think of Chernobyl, 3 Mile Island, and Fukushima, the accidents that have dominated public memory of nuclear power. Fusion is genuinely different in its risk profile, but communicating that difference clearly and maintaining public trust through transparent reporting of both progress and setbacks is a challenge that the fusion community has not always handled well. The optimistic timelines that have repeatedly proven over-optimistic have contributed to a degree of public and political skepticism that makes securing sustained investment more difficult. Building credibility through clear communication, achieved milestones, and honest acknowledgement of remaining challenges is as important to the success of fusion as any piece of physics or engineering. Historical comparison with other energy technologies is instructive. Nuclear fission reactors were first demonstrated to produce electricity in 1951 at the experimental Breeder Reactor 1 in Idaho. The first commercial nuclear power plant, Calder Hall in the United Kingdom, began operation in 1956, just 5 years later. This transition from first demonstration to commercial operation was extraordinarily fast by the standards of complex energy infrastructure. The reasons were partly technological. The basic physics was well understood. The engineering challenges were significant, but not fundamentally novel, and partly political and strategic. Governments in the United States, United Kingdom, France, and Soviet Union were heavily motivated to develop nuclear power as part of their national security and industrial programs. Fusion lacks that last driver. There is no fusion weapons stockpile to justify massive national investment in fusion technology as a national security imperative. And the physics challenges are, arguably, harder than those of fission. Plasma confinement adds a dimension of complexity that fission, for all its challenges, does not face. The development trajectory of fusion has therefore been slower, and appropriately so. The comparison with renewable energy is also instructive, though different in character. Solar photovoltaics were first demonstrated to generate electricity efficiently in the 1950s at Bell Laboratories with an efficiency of 6%. Decades of incremental improvement followed, driven by learning effects, economies of scale, and sustained public investment in research. Commercial solar costs remained very high through the early 2000s. Then, beginning roughly in 2010, costs began falling rapidly as manufacturing scale increased, driven primarily by deployment in Germany, China, and the United States. By the early 2020s, utility-scale solar had become the cheapest new electricity source in history in most markets, with costs falling by over 90% in a decade. Fusion cannot replicate this trajectory exactly. It is a more complex technology with more fundamental remaining uncertainties than solar photovoltaics had by 2010. But the solar story illustrates that technologies that appear stuck at high cost for decades can, under the right conditions, undergo rapid cost reductions once the technology is sufficiently mature and scale effects kick in. The question for fusion is whether the remaining technical demonstrations, particularly sustained burning plasma in ITER and net energy gain in smaller private devices, will constitute sufficient maturity to begin the deployment trajectory that drives costs down. The question of what role fusion will play in a decarbonized global energy system depends on timing as much as capability. If the first commercial fusion plants are operating in the mid-2030s, they enter a world where decarbonization is still underway and competitive pressure from other clean technologies, while significant, does not necessarily foreclose fusion's market. If fusion's commercial debut slips to the 2040s or beyond, the energy transition will be further advanced. The remaining decarbonization challenge will be focused on the hardest sectors: heavy industry, long-haul aviation and shipping, seasonal energy storage, and the market for fusion will be shaped by those specific needs rather than grid electricity in general. Either scenario is plausible. The physics does not dictate the timeline. The engineering and economics do, and both of those depend on decisions made by engineers, investors, policymakers, and the public about how much effort and capital to direct toward the problem. What is not in doubt is the scale of what would be achieved if fusion does become commercially viable. Consider the following. Global energy consumption in 2023 was approximately 600 exajoules, 6 times 10 to the power of 20 joules. The energy content of 1 gram of deuterium-tritium fuel is approximately 337 megajoules. Meeting global energy demand entirely from deuterium-tritium fusion would require roughly 1.8 million kilograms, 1,800 tons, of deuterium-tritium fuel per year. Deuterium can be extracted from seawater essentially without limit. The world's accessible lithium reserves, which would be used to breed tritium, are estimated at tens of millions of tons, representing a fuel supply that even in a fully fusion-powered global economy would last for centuries. The environmental footprint of a fusion economy would be fundamentally different from both fossil fuels and fission. No carbon dioxide, no sulfur dioxide, no nitrogen oxides, no long-lived radioactive waste requiring geological timescale sequestration, some radioactive structural components requiring managed disposal over decades. Tritium, which is radioactive with a 12-year half-life, would need to be handled carefully, but is already managed at much larger scales in the existing nuclear industry. The land footprint per unit of energy would be small compared to wind and solar farms at equivalent generation capacity, though this advantage depends on actual reactor power density and capacity factors that have not yet been demonstrated at commercial scale. The intellectual history of fusion is a story of people who were right about the fundamental physics, right that stars run on nuclear fusion, right that deuterium-tritium is a viable fuel combination, right that magnetic confinement can in principle hold a plasma long enough to achieve net energy gain, but consistently wrong about how quickly the engineering challenges could be overcome. The lesson of that history is probably not that the engineers were incompetent. It is that the challenges were harder than anticipated, and that anticipating the difficulty of large, complex engineering challenges is itself very difficult. The fusion community today is older and wiser about this. The private companies making bold timeline claims are, for the most part, aware of the history of over-optimistic fusion predictions and are making explicit bets that new materials, new computational tools, and new management approaches will change the pace. Some of those bets will be wrong, some possibly will be right. What the influx of private capital and the diversity of approaches has created is a situation in which the cost of being wrong about any particular approach is lower than it used to be. There are multiple paths being pursued simultaneously, and the success of any one of them would be transformative. The next 5 years will be decisive in ways that the previous 20 were not. ITER's magnet systems will be fully assembled. Spark will achieve first plasma and begin its experimental program. Helion will either deliver electricity to Microsoft or acknowledge that its 2028 deadline was not achievable. Commonwealth Fusion Systems will either begin construction of ARC or revise its roadmap. The Chinese fusion program, which has moved aggressively in recent years with its East and CFETA devices, will publish results from experiments at conditions closer to reactor relevance than any previous device. And the results from these programs will, for the first time in the history of fusion, arrive fast enough and close enough together to give the scientific community investors and policymakers a clear picture of which approaches are working and which are not. The next 30 years, the same interval that fusion has been said to be 30 years away for the better part of a century, will determine whether fusion joins solar, wind, and nuclear fission as a commercial energy source, or whether it remains a technology of profound scientific interest and perpetually elusive commercial viability. The physics is not the limiting factor. The engineering is, and engineering, unlike physics, responds directly to the resources directed at it. Eddington's reservoir is still waiting to be tapped. The tools available to the engineers trying to tap it today are better than at any point in the history of the effort. Whether that is enough is the great empirical question of energy technology in the 21st century. The answer is being worked out right now in plasma chambers and computational models and manufacturing facilities and regulatory offices by thousands of people in dozens of countries who believe that what the sun does so effortlessly every second is something that a sufficiently determined and sufficiently well-funded civilization can learn to do on its own terms. They may be right, or the engineering challenges may again prove harder and longer to solve than the present optimism suggests. The history of fusion councils, humility about timelines, the physics council's persistence about the goal, and the urgency of the energy challenge councils that this is precisely the moment to be directing more resources, more talent, and more sustained attention toward one of the most consequential technological questions of our time, the story of how we came to understand the specific nuclear reactions inside stars is a story of extraordinary detective work carried out over the first half of the 20th century, with contributions from physicists working in circumstances ranging from comfortable university offices to the desperate urgency of the Manhattan Project. Understanding that history adds important depth to the current state of fusion research because the physical problems that engineers are still wrestling with today were first identified by theorists who recognized them decades ago. In 1928, the Russian-American physicist George Gamow applied the newly developed mathematics of quantum mechanics to nuclear physics and worked out the theory of alpha decay, the emission of an alpha particle from a radioactive nucleus. His key insight was that the alpha particle could tunnel through the Coulomb barrier surrounding the nucleus, escaping even though its kinetic energy was insufficient to surmount the barrier classically. This tunneling calculation was immediately recognized as applying in reverse to fusion reactions. If a particle can tunnel out of a nucleus, another particle can tunnel in, and the probability of this tunneling determines the rate at which fusion reactions can occur. In 1929, Robert Descor Atkinson and Fritz Houtemans used Gamow's tunneling theory to calculate the rate at which proton-proton fusion could occur inside stars. Their calculations confirmed Eddington's speculation. Hydrogen fusion into helium could, with the tunneling effect factored in, produce enough energy to power the sun over its observed lifetime. The calculations were not yet precise enough to identify the exact reaction chain operating inside the sun, but they established the basic theoretical framework. Stars are quantum mechanical devices that exploit the wave nature of subatomic particles to do something that classical physics says is impossible. The specific reaction chain, the proton-proton chain, and the competing carbon-nitrogen-oxygen cycle was worked out in 1938 and 39 by Hans Bethe, a German-American physicist who would later play a central role in the Manhattan Project. Bethe's paper on stellar energy production, published in 1939, was remarkably comprehensive. It correctly identified the dominant energy source in sun-like stars as the proton-proton chain, and correctly identified that in more massive, hotter stars, the carbon-nitrogen-oxygen cycle, in which carbon, nitrogen, and oxygen nuclei act as catalysts for converting hydrogen to helium, becomes dominant. For this work, Bethe received the Nobel Prize in Physics in 1967. The proton-proton chain that Bethe analyzed is not a single reaction, but a sequence. The first step, two protons combining to form deuterium, with one proton undergoing beta decay into a neutron, a positron, and a neutrino, is the rate-limiting step. It is the step that takes, on average, 10 billion years per proton, and it is the step that makes proton-proton fusion on Earth completely impractical. The subsequent steps, deuterium plus a proton forming helium-3, two helium-3 nuclei fusing to form helium-4 and releasing two protons, are much faster, occurring on timescales of seconds to millions of years at solar core conditions. Bether's analysis also revealed why alternative reaction pathways, using the heavier hydrogen isotopes deuterium and tritium, are so much faster. They bypass the slow weak force beta decay step entirely. The rate-limiting step in the proton-proton chain is the conversion of a proton into a neutron by the weak force. Remove that step by using nuclei that already contain the right number of neutrons, and the reaction rate increases by many orders of magnitude. This is why deuterium-tritium fusion is the focus of virtually all current engineering efforts. It is not the reaction that powers the sun. It is a reaction that shares the sun's basic physics, but avoids the sun's most severe kinetic bottleneck. The experimental confirmation that heavy hydrogen nuclei could be fused came in 1934 from work by Mark Oliphant at the Cavendish Laboratory in Cambridge, working under Ernest Rutherford. Oliphant fired beams of deuterium nuclei at deuterium targets and detected the products, helium-3, tritium, and high-energy neutrons, proving that nuclear fusion between deuterium nuclei was physically achievable under laboratory conditions. This was the first experimental demonstration of nuclear fusion on Earth, predating the first nuclear fission demonstration by several years. Rutherford was characteristically skeptical about practical applications, reportedly saying that anyone who expected to extract energy from atomic transmutations was talking moonshine. He was not entirely wrong. The practical challenges were, as it turned out, enormous. But the physics was real, and Oliphant's demonstration gave fusion science its first experimental foundation. The path from Oliphant's laboratory experiment to the hydrogen bomb took less than 20 years. The key figures were Edward Teller, who conceived the thermonuclear weapon design known as the Super, Stanislaw Ulam, who solved the critical compression problem that made it feasible, and Hans Bethe, who contributed theoretical analysis of the device's physics. The first thermonuclear device was tested by the United States in November of 1952. Its yield was approximately 10.4 megatons, 800 times greater than the bomb dropped on Hiroshima. The Soviet Union followed with its own hydrogen bomb test in August of 1953, demonstrating that the physics of thermonuclear weapons was not a monopoly. The hydrogen bomb demonstrated conclusively that deuterium-tritium fusion could release energy in quantities, dwarfing anything achievable by chemical or fission reactions. The challenge was immediate and obvious: how to achieve the same fusion in a controlled, sustained manner rather than in a microsecond explosion. Classified fusion research programs began in the United States, the Soviet Union, and the United Kingdom almost immediately after the hydrogen bomb tests. The first serious magnetic confinement experiments, the pinch machines, which used pulsed magnetic fields to squeeze plasma, produced early results that seemed promising. And in 1958, the United States, the Soviet Union, and the United Kingdom simultaneously declassified their fusion programs and shared preliminary results at the first United Nations Conference on the peaceful uses of atomic energy in Geneva. The declassification was motivated partly by scientific openness and partly by the recognition that fusion power was still so far from practical, realization that there was no military advantage in secrecy. The consensus in 1958 was that practical fusion power was perhaps 20 years away. That estimate would prove incorrect, but the scientific community's willingness to share results internationally established a cooperative tradition in fusion research that has, with some interruptions and tensions, persisted to the present day, culminating in ITER as the largest peacetime scientific collaboration in history. The tokamak design emerged from Soviet fusion research in the late 1950s and early 1960s. The key innovation was the combination of a strong toroidal magnetic field generated by external coils with a poloidal field generated by a large current flowing through the plasma itself. This combination produces helical magnetic field lines that wind around the torus in a pattern that, over time, averages out the drift forces that would otherwise push the plasma into the wall. The first tokamak, called T1, was built at the Kurchatov Institute in Moscow and began operation in 1958. Its plasma temperatures were modest by later standards, but the basic confinement concept worked better than any previous approach. Western scientists were initially skeptical of Soviet tokamak results, which seemed surprisingly good. In 1969, a British team visited the T3 tokamak in Moscow and made independent measurements that confirmed the Soviet claims: plasma temperatures of 10 million degrees Celsius, far higher than anything achieved in Western pinch machines. This verification triggered a rapid switch in the priorities of Western fusion programs toward the tokamak design. Fusion research in the 1970s and 1980s was dominated by progressively larger tokamaks. The Alcator series at MIT, the PLT and TFTR at Princeton, the jet reactor in the European Union, that explored the physics of plasma confinement at increasingly high temperatures, densities and plasma currents. TFTR, the tokamak fusion test reactor at Princeton, conducted the first experiments with deuterium-tritium fuel in 1994, producing a then world record 10.7 megajoules of fusion energy. JET followed with its own deuterium-tritium experiments and achieved a world record of 22 megajoules in 1997. These results confirmed that deuterium-tritium fusion in a tokamak was not just theoretically possible, but experimentally demonstrated. The missing piece, net energy gain, remained elusive because the plasma heating power required to reach fusion conditions still exceeded the fusion power produced. But the trend was encouraging. The decision to build ITER was made in the context of these experimental successes. ITER, originally the acronym, stood for International Thermonuclear Experimental Reactor, though the collaboration later adopted the interpretation that ITER means path or journey in Latin, was conceived in the 1980s during the Reagan-Gorbachev summit in Geneva, when the two leaders proposed a joint scientific project as a symbol of international cooperation. Fusion was chosen as the field, and the design of ITER was carried out collaboratively through the 1990s. The project has been through several redesigns and significant cost increases since its formal inception, but it has survived all of them, a testament to the sustained political and scientific commitment of the 35 participating nations. The scale of ITER is difficult to appreciate from descriptions alone. The device stands roughly 30 meters tall. The tokamak's plasma volume is 840 cubic meters, large enough to contain 3 Olympic swimming pools. The central solenoid magnet, the electromagnet at the heart of the device that induces the plasma current, will be the most powerful pulsed magnet in the world, capable of producing fields of 13 Tesla. The superconducting coils that generate the toroidal field must be cooled to minus 269 degrees Celsius using liquid helium. The plasma they confine will be at 150 million degrees Celsius, the largest temperature gradient in any human-made structure. Roughly 1 million components will be manufactured by the 35 member nations and shipped to Cataract for assembly. The total mass of the machine, including its cryostat and support structures, will exceed 23,000 tons. ITER's scientific mission is to demonstrate Q equal to 10 times more fusion power out than heating power in, and to explore the physics of a burning plasma in which the heat produced by alpha particles from the fusion reaction sustains the plasma temperature without the need for external heating. This burning plasma regime has never been achieved in any previous device, and the physics of how a plasma behaves when its own fusion products are the dominant heating source is not fully understood from first principles. Surprises are expected, and those surprises, and the understanding gained from them, will be among ITER's most valuable scientific outputs. The international character of ITER means that the 35 participating nations will share in both the costs and the scientific results. Each nation contributes components manufactured within its own industrial base: the magnets from the European Union and Japan, the vacuum vessel sectors from the European Union and Korea, the heating systems from different members, the diagnostics from yet others. This approach distributes manufacturing costs and builds industrial expertise in fusion technology across multiple countries, which is an important foundation for a future fusion industry. It also introduces complexity. Tolerances must be maintained across components manufactured on 3 different continents, and coordination across multiple industrial and regulatory jurisdictions is inherently more complicated than single-nation procurement. The private fusion companies have a different model. They can make decisions quickly, iterate on designs without international committee approval, and focus resources on the specific technical problems they believe are most tractable. The trade-off is that they must convince private investors, who expect returns on timescales of years to a decade, not the decades that characterize major government science projects, that their approach is viable. This creates a selection pressure for approaches that can demonstrate progress quickly and that have plausible near-term commercial applications. Commonwealth Fusion, Systems' strategy of focusing on high-temperature superconducting magnets to enable a smaller, faster-to-build device is a classic expression of this logic. If the key constraint in tokamak fusion is the strength and cost of the magnetic field, then the availability of new superconducting materials that can generate stronger fields at lower cost changes the economics of the entire enterprise. Rebco tape, the yttrium-barium-copper oxide superconductor on which CFS's magnets are based, was not commercially available in sufficient quantities for magnet applications even 15 years ago. The material science advances that made it available are the result of decades of research in condensed matter physics aimed primarily at understanding the phenomenon of high-temperature superconductivity rather than at fusion applications. This is a common pattern in technology. Enabling breakthroughs often come from entirely unrelated fields of research. The same dynamic applies to advances in computational power. The plasma simulations that guide reactor design today run on supercomputers that would have been inconceivable to the fusion researchers of the 1980s. The ability to simulate plasma behavior in 3 dimensions over time intervals comparable to fusion pulse lengths, to model the interaction between plasma and wall materials, and to optimize magnetic field configurations without building expensive physical experiments. All of this computational capability is enabling a much faster design cycle than was possible in previous decades. Coupled with machine learning tools that can extract physical understanding from the enormous datasets produced by plasma diagnostics, the intellectual infrastructure available to fusion researchers today is qualitatively different from what was available even 2 decades ago. The question of whether this improved infrastructure is sufficient to bridge the remaining gap between where fusion technology stands today and commercially viable power generation is not one that can be answered by analysis alone. It requires experiments. The experiments are underway, and the results, accumulating over the next decade, will provide an empirical answer to a question that theory and optimism alone cannot resolve. One aspect of fusion research that rarely receives adequate attention in popular accounts is the diagnostic infrastructure required to understand what is happening inside a burning plasma. A fusion plasma at 150 million degrees Celsius cannot be probed with conventional instruments. No physical probe can withstand those conditions. Instead, physicists infer the properties of the plasma from radiation and particles that it emits, from the scattering of carefully aimed laser or microwave beams, and from the response of the plasma to externally applied perturbations. Building and operating these diagnostic systems is itself a major scientific and engineering enterprise. The plasma in a modern tokamak emits radiation across a vast range of wavelengths. Visible light comes from impurities swept off the wall and heated to fluorescence by the plasma. X-rays in the kilo-electron-volt range come from Bremsstrahlung, radiation produced when electrons are decelerated. By the electric fields of ions, the spectrum of this radiation encodes information about electron temperature. Neutrons produced by fusion reactions carry information about plasma density, temperature, and fusion rate. Gamma rays produced by activation of plasma-facing materials or nuclear reactions between energetic plasma ions reveal details about particle energy distributions. Each diagnostic system requires different detectors, different sightlines into the plasma, different data acquisition systems, and different analysis techniques. In ITER, more than 40 different diagnostic systems will be installed, monitoring everything from electron temperature and density profiles to the shape of the plasma boundary, the composition of plasma impurities, the distribution of fast alpha particles from fusion reactions, and the structural integrity of plasma-facing components. Each diagnostic must be designed to survive the neutron and radiation environment inside the device, function reliably for years of operation, and provide data at sufficient time resolution to detect and respond to plasma instabilities before they develop into disruptions. The neutron diagnostics are particularly important in a burning plasma because the neutron emission is directly proportional to the fusion reaction rate, and its spatial profile reveals where in the plasma the fusion is occurring. Detecting individual high-energy neutrons against a background of scattered neutrons and gamma rays in a high radiation environment requires sophisticated detector systems, typically scintillation crystals or liquid scintillators coupled to photomultipliers, placed outside the neutron shielding and connected to the plasma interior through carefully designed neutron channels. The measurement of alpha particle behavior, how the energetic helium-4 nuclei produced by fusion heat the plasma, where they slow down and deposit their energy, and how they eventually escape from the plasma, is one of the most important new physics questions that ITER will address. Alpha particles are born with energies of 3.5 mega-electron volts, far above the thermal energy of the plasma. They slow down by Coulomb collisions with the bulk plasma electrons and ions over a timescale of milliseconds to seconds, depending on plasma conditions. If they slow down in the core of the plasma, their energy goes into heating the core, exactly what is needed to sustain the burning plasma. If instabilities in the plasma cause them to escape before they slow down, they carry their energy out of the plasma and into the wall, potentially damaging plasma-facing components and reducing the heating efficiency. Managing alpha particle confinement is therefore crucial to the performance of a burning plasma reactor. The instabilities most relevant to alpha particle confinement are a class of electromagnetic waves called Alphen eigenmodes, oscillations in the magnetic field, structure that can resonantly interact with fast alpha particles and drive them outward. These modes are driven by the velocity gradient of the alpha particle population. There are many more particles at the freshly born 3.5 mega-electron-volt speed than at lower speeds, and this non-equilibrium distribution can feed energy into the waves. Understanding and predicting the conditions under which Alphen eigenmodes are excited, and how strongly they scatter alpha particles, is an active area of theoretical and experimental research. The plasma-facing components of a fusion reactor must also manage the steady flux of heat and particles from the plasma edge. In a tokamak, the plasma is not perfectly confined. A small fraction of the plasma particles continuously leak outward through the magnetic field, reaching the plasma-facing components. These particles must be absorbed and neutralized, and the helium ash produced by fusion reactions, alpha particles that have slowed down and become neutral helium atoms, must be evacuated from the plasma before they dilute the deuterium-tritium fuel. The diverter handles this exhaust, channeling plasma flow into a cooler region where neutralization occurs, and where the helium can be pumped away. In ITER, the diverter will be subject to heat loads of up to 10 megawatts per square meter in steady state, with transient loads during edge plasma events potentially reaching hundreds of megawatts per square meter. The diverter targets will be made of tungsten, chosen for its high melting point and good thermal conductivity. The water cooling systems behind the tungsten tiles must remove heat at rates that challenge the limits of heat exchanger design. Managing this heat load over operational lifetimes of months to years, while simultaneously handling the radioactive environment and remotely maintaining the components. Using robotic systems, because the activated structure cannot be accessed by human workers after neutron bombardment, is one of the most demanding aspects of tokamak engineering. Remote maintenance is a capability that deserves specific mention, because it is easy to overlook. After even a few months of operation at significant fusion power, the structural materials of a fusion reactor become sufficiently radioactive that human workers cannot enter the reactor hall. All maintenance, component replacement, and inspection must be carried out by robotic systems operating through limited access ports. The manipulators must be precise enough to handle components weighing tons to tolerances of millimeters, operate within a constrained geometry, and be themselves radiation hardened against the environment in which they work. Remote handling systems for ITER are being developed and tested on full-scale mock-ups of the reactor geometry, and they represent a significant engineering program in their own right. The helium produced by fusion reactions, helium-4 from the main deuterium-tritium fusion, and helium-3 from tritium decay, and as a product of some deuterium-deuterium reactions, must be continuously removed from the plasma. Helium does not fuel the fusion reaction. If helium accumulates in the plasma, it dilutes the deuterium and tritium fuel, reducing the fusion rate and eventually quenching the reaction. The cryogenic pumping systems that remove helium from the diverter must handle both hydrogen isotopes, which are recycled back to the plasma, and helium, which is exhausted from the machine. Separating helium from hydrogen isotopes in the diverter exhaust stream is a continuous process that must operate reliably for years. The fuel cycle of a fusion reactor, the systems that process, store, and inject deuterium and tritium, is itself a substantial engineering system. Tritium is radioactive and must be handled with care throughout the fuel cycle. The tritium inventory of a fusion reactor, the amount of tritium present in the facility at any time, distributed between storage, the blanket, the plasma, and the processing systems, determines the regulatory requirements and emergency planning zones. Minimizing the tritium inventory while maintaining reliable fuel supply is an important design objective for fusion reactors, particularly for community acceptance. For all these engineering challenges, plasma-facing materials, remote maintenance, diverter heat loads, tritium breeding, tritium fuel cycle, alpha particle physics, ITER is designed to provide the first data at reactor-relevant scale. The answers it provides will directly inform the design of demonstration reactors and eventually commercial plants. Some of the answers will be favorable, some will reveal unforeseen problems that require further innovation. This is how engineering at the frontier works. ITER is expensive, and it has taken longer to build than hoped, but it is designed to answer questions that cannot be answered any other way. The question of how quickly the gap between ITER's scientific mission and commercial power generation can be closed depends on decisions that are being made right now. The fusion roadmap in Europe envisions a demonstration reactor called DEMO that would follow ITER, produce net electrical power, and demonstrate the complete nuclear fuel cycle, including tritium breeding. DEMO would then be followed by commercial fusion plants. The timeline for this sequence: ITER experiments in the 2030s, DEMO in the 2040s or 50, commercial plants in the 2050s or beyond, is not the timeline that the climate crisis demands. This is why the private sector push matters. Commonwealth Fusion Systems, Helion, TAI Technologies, General Fusion, Eni-backed Renaissance Fusion, and dozens of other companies are not trying to insert themselves between demo and commercial plants. They are trying to demonstrate net energy gain and commercial feasibility on a much faster timescale, compressing what the public roadmap envisions as a 40-year sequence into a 10 to 15-year program. Some will fail. The history of deep technology startups strongly suggests that most will fail. But the diversity means that failure of any individual company does not end the pursuit, and the public roadmap itself is not standing still. The scientific and engineering understanding gained from each new experiment, JET's deuterium-tritium record, the National Ignition Facility's ignition demonstration, the ongoing experiments at Korea's K-Star and China's East tokamaks, continuously updates the basis on which the next steps are planned. K-Star, the Korean superconducting tokamak advanced research reactor in Daejeon, South Korea, has set records for the duration of high-temperature plasma operation, achieving a plasma of 100 million degrees Celsius for 48 seconds in 2024, a record for sustained high-temperature operation in any tokamak. East, the experimental advanced superconducting tokamak operated by the Chinese Academy of Sciences in Hefei, has also demonstrated record plasma durations at high temperatures. These results demonstrate that the technical challenge is not merely reaching high temperatures, but sustaining them reliably, which is the regime that a commercial reactor must operate in continuously. The international nature of the scientific results, with record-setting experiments happening in Korea, China, the United Kingdom, and the United States, reflects the genuinely global character of fusion research. Every major industrial nation with a significant physics research program has invested in fusion. The reasons are both scientific. Fusion is among the most challenging and intellectually rich problems in applied physics, and strategic nations that develop fusion technology will have significant advantages in energy security and, potentially, in the industries that grow around fusion technology. Looking at the full arc of the story, from Eddington's 1920 conjecture about the energy source of stars, through the quantum mechanical understanding of nuclear reactions developed in the 1920s and 30s, through the experimental demonstrations of the 30s and 40s, through the decades of magnetic and inertial confinement research, through the hydrogen bomb and the era of classified fusion programs, through the international cooperative programs of the Cold War and post-Cold War eras, and now into the current moment of private investment and accelerating experimentation. What is most striking is how the fundamental physics has remained stable throughout. The equations governing plasma behavior were written down in the 1940s and 50s. The cross-sections for deuterium-tritium fusion were measured in the 1950s and have not needed revision. The basic design principles of tokamaks were established in the 1960s. What has changed over the decades is not the physics, but the engineering tools available to work with it. The strength of magnets, the power of lasers, the precision of plasma diagnostics, the capability of control systems, and above all, the computational power available to simulate and optimize designs. The transition from an era in which fusion was constrained primarily by what physics knowledge was available to an era in which the physics is well understood and the constraints are primarily engineering and economics is a significant and underappreciated shift. Physics problems have clear answers that can be found through theory and experiment. Engineering problems have solutions that depend on the resources, creativity, and iteration capacity devoted to finding them. The shift means that the pace of progress in fusion is now determined primarily by human choices about investment and prioritization, not by the pace at which nature reveals its secrets. Those human choices are being made in boardrooms and government ministries and university laboratories and startup incubators right now. They will determine whether fusion energy arrives in time to play a meaningful role in the decarbonization of the global economy, or whether it arrives later as a technology that is genuinely valuable, but that came after the hardest part of the energy transition was already done by other means. Either outcome would represent an extraordinary achievement. Replicating, in a controlled and useful form, the process that powers every star in the observable universe would be among the most significant technological accomplishments in human history. The fact that it is taking longer than hoped does not diminish that achievement. The fact that it is still being pursued, with more resources and more approaches than ever before, suggests that the people doing the pursuing believe, with reasons that have grown stronger year by year, that it is achievable. It is worth pausing to consider what net energy gain actually means in the context of a power plant, because the terminology is frequently misused in popular coverage of fusion milestones, and the misuse creates unrealistic expectations that contribute to the credibility problem the fusion field faces. When physicists talk about fusion energy gain, the parameter Q they are comparing fusion energy produced to the energy used to heat the plasma. This is a measure of plasma performance. It tells you whether the plasma physics is working. Q equal to 1, break even in the physics sense, means the fusion reactions produce as much energy as was deposited into the plasma to heat it. Q equal to 10, ITER's goal, means 10 times as much fusion energy out as heating energy in. But a power plant must also supply electricity to the grid. The relevant figure is not physics Q, but engineering Q, sometimes written Q engineering, which compares the electrical energy delivered to the grid to the total electrical energy consumed by the plant, not just by the plasma heating, but by the magnets, the cooling systems, the plasma control systems, the tritium processing, the facility lighting, the instrumentation, everything. For most tokamak designs, the parasitic power loads, the electricity consumed by the plant's own systems, are substantial. Even at Q equal to 10 in the plasma sense, the overall electrical efficiency of the plant, accounting for the efficiency of converting fusion heat to electricity and the parasitic loads, would likely yield a Q engineering of somewhere between 1 and 3 for a first-generation commercial plant. Q engineering of 1, barely break even in the power plant sense, would not be economically viable. The plant would consume as much electricity as it delivers, leaving no net output for sale. To be commercially competitive, a fusion plant needs to deliver electricity to the grid at a cost comparable to alternative sources. Given the capital-intensive nature of fusion plants, the expensive magnets, the complex plasma systems, the robust radiation shielding, the tritium handling infrastructure, the electricity cost from fusion depends strongly on how often the plant can run, how long the components last before requiring replacement, and how much the capital cost is. These economic parameters are, at this point in fusion's development, largely unknown. They will not be known until demonstration plants are built, operated, and subjected to the realities of real-world operating costs. This economic uncertainty is not unique to fusion. The first nuclear fission plants faced the same uncertainty. The first commercial reactors were built partly as demonstrations of feasibility and partly on faith that costs would fall as the technology matured. In some cases, that faith was rewarded. French nuclear power, built out in a massive standardized program in the 1970s and 1980s, delivered some of the cheapest electricity in Europe for decades. In other cases, most recent nuclear builds in Western countries, costs have proven higher than anticipated, with projects like the Vogtle plant in Georgia in the United States finishing well over budget and years late. The difference between the cheap French program and the expensive recent Western builds involves lessons that fusion developers are actively trying to absorb. The French program succeeded partly because of standardization, building the same reactor design repeatedly so that learning effects could reduce construction cost and time, and partly because of a capable, experienced workforce and industrial supply chain. Recent Western nuclear builds have suffered from the loss of those capabilities over decades of low construction activity, which meant rebuilding industrial and workforce knowledge from scratch at high cost. The fusion industry faces the same challenge of building industrial capability from a low base. And the diversity of competing reactor designs, while valuable for exploring the technology space, does not naturally lend itself to the standardization that drives cost reduction. The optimal strategy for fusion. Commercialization, if one could design it from scratch, might involve exactly the kind of phased approach that Commonwealth Fusion Systems has outlined. A demonstration device that proves net energy gain and burning plasma physics, followed by a pre-commercial plant that demonstrates economic operation, followed by series production of standardized commercial plants that drive costs down through learning effects. The challenge is that each step requires enormous capital investment before the commercial returns from previous steps are clear. This is the valley of death that many deep technology ventures fail to cross, and it is why government involvement, either as direct, funder or as anchor customer, will likely be necessary to bridge the gap between demonstrated scientific feasibility and commercially viable deployment. The United States Department of Energy recognized this in 2023 when it launched a program to support the development of fusion pilot plants through partnerships between the public sector and private fusion companies. The program, called the Milestone-Based Fusion Development Program, awarded initial funding to 8 companies to develop conceptual designs for fusion pilot plants. This kind of public-private partnership, government funding to de-risk early development stages, private capital to drive toward commercialization, is a model that has worked in other deep technology domains, including semiconductor development, commercial space launch, and advanced nuclear fission. Applying it to fusion is a policy choice that reflects growing institutional recognition that the public interest in fusion's success justifies public investment to accelerate it. The question of whether fusion is worth the investment, compared to alternatives for decarbonizing the global energy system, deserves honest engagement. Solar, wind, batteries, energy efficiency, and grid modernization are already deployable and rapidly declining in cost. Significant additional investment in these technologies can deliver large amounts of clean electricity in the near term. Fusion, by contrast, cannot deliver commercial electricity for at least a decade and possibly longer. The argument for continued fusion investment despite this gap rests on 2 premises. First, there are energy services that variable renewables and batteries struggle to provide economically. Firm baseload power in regions with limited solar and wind resources, high-temperature industrial heat at scales that electric resistance heating cannot efficiently provide, and very long-duration energy storage for seasonal variations in renewable output. These are real gaps, and fusion could address them if it becomes commercially available. Second, the clean energy transition will not be complete in any decade. Decarbonizing heavy industry, steel, cement, chemicals, requires either very large amounts of firm clean electricity or process heat at temperatures that current electric technologies cannot provide efficiently. Aviation and shipping are currently very difficult to decarbonize because the energy density of hydrogen, ammonia, or synthetic liquid fuels is substantially lower than jet fuel or bunker fuel, requiring large penalties in range or payload. Fusion-powered electricity production of green hydrogen or synthetic fuels for these applications could be economically competitive even if fusion electricity is more expensive than solar or wind, because the alternative is also expensive. These arguments are not speculative. They reflect real engineering constraints in the energy system. But they do require fusion to actually achieve commercial deployment, something that has not yet happened, and that depends on solving the remaining engineering challenges. The case for investing in fusion is therefore a case for hedging. The world cannot know today exactly how difficult it will be to fully decarbonize all energy sectors with the technologies currently available. And fusion offers an option value, the ability to tap a source of energy that, if the engineering can be made to work at scale, is nearly unlimited and produces no carbon dioxide. Option value is a concept borrowed from financial economics, but it applies naturally to technology investment. Spending money to develop a technology that might not be needed but that would be very valuable if it is rational if the cost of developing the technology is small relative to the potential value if it is needed. Fusion research globally costs roughly $2 to $3 billion per year across public and private programs. The global energy economy is worth many trillions of dollars annually. If fusion even modestly improves the prospects for full decarbonization of that economy, the option value of the investment is enormous relative to its cost. This framing, fusion as an option on a fully decarbonized energy system, is increasingly how sophisticated energy analysts are thinking about the public justification for fusion investment. It is a more honest framing than the promise of limitless, cheap, clean energy, which fusion's history suggests should be stated with more qualification than it typically receives. And it is a framing that justifies sustained investment even in the face of persistent timeline uncertainty. The scientific community pursuing fusion is not unaware of these broader considerations. Plasma physicists and fusion engineers understand the energy context in which their work exists. The growing emphasis on near-term timelines and commercial relevance in the fusion research agenda, visible in the design choices of private companies, in the policy framing of programs like the Department of Energy's Milestone program, and in the public communications of major fusion projects, reflects an understanding that scientific achievement is necessary but not sufficient. Fusion must deliver commercially, at scale, before the energy transition is complete, if it is to justify the investment that is being made in it. Whether it will is the question. The answer will come from physics experiments and engineering demonstrations over the next decade. It will come from the first plasma in ITER, from the first net energy gain in Spark, or a private competitor, from the first demonstration of sustained burning plasma, where the fusion products themselves are the dominant heating source. It will come from tritium breeding experiments in test blanket modules, from neutron damage measurements in irradiated materials, from the operation of tritium processing and fuel cycle systems at scale. All of these experiments are planned. Some are already underway. The data they will produce is the empirical foundation on which the next generation of fusion reactors, demonstration plants, and after them, commercial plants, will be built. The outcome is not predetermined, but it is more knowable than it has ever been. The physics is understood. The engineering challenges are identified. The tools are better than they have ever been. The investment is larger than it has ever been. The number of approaches being pursued simultaneously is greater than it has ever been. Every previous generation of fusion researchers believed that the fundamental breakthroughs were just around the corner and found themselves surprised by the difficulty of the engineering. The current generation has the advantage of inheriting all that accumulated difficulty and all the partial solutions developed to address it. The surprises will come. They always do. But the base of knowledge from which the current generation works is incomparably richer than what was available to any of their predecessors. The sun will keep burning, regardless of what we decide to do here. Its fusion reactor will operate for another 5 billion years or so, converting 600 million tons of hydrogen to helium each second, emitting 386 trillion joules into space, with 175 quadrillion joules of that reaching our planet in the form of sunlight every second. That energy sustains every living thing on Earth. It has done so for 4.5 billion years. It built us, shaped our evolution, powered our civilizations, and ultimately inspired us to ask the question of how it works. The answer to that question, worked out over the first half of the 20th century by a succession of brilliant and curious people, turned out to be quantum mechanics in service of nuclear physics. Particles tunneling through energy barriers that classical physics says are impassable, producing energy through a conversion of mass so total and complete that it defies the ordinary intuitions of everyday experience. The answer was more exotic and more profound than anyone expected when Eddington first raised the question in 1920. The answer to the question of whether we can do what the sun does, controlled, sustained, commercially useful fusion on Earth, is still being worked out. The first chapter, establishing the physics, took about 30 years. The second chapter, developing the engineering to the point of demonstrating scientific feasibility, has taken about 70 years. The third chapter, commercial deployment, is just beginning. How long it takes and what it delivers will depend on choices made by engineers, scientists, investors, policymakers, and the broader public over the coming decades. The reservoir is inexhaustible. The store is well nigh limitless, if only it could be tapped. We are closer to tapping it than we have ever been. We have not yet succeeded. The distance between those two sentences is where the most consequential work in energy technology today is being done. There is a specific phenomenon in fusion plasmas that illustrates, better than almost anything else, the combination of elegance and frustration that characterizes the field. It is called the H mode, short for high confinement mode, and its discovery was an accident. In 1982, physicists operating the ASTEX tokamak at the Max Planck Institute for Plasma Physics in Garching, Germany, were experimenting with neutral beam heating, injecting high-energy beams of hydrogen atoms into the plasma to heat it from the outside. As they increased the heating power, they observed something unexpected. At a certain threshold power, the plasma confinement quality suddenly and dramatically improved. The energy confinement time, the characteristic timescale over which the plasma loses its heat to the walls, roughly doubled in a matter of milliseconds. The plasma spontaneously organized itself into a state with much lower transport of heat from the core to the edge. This transition was called the L to H transition, where L stands for low confinement mode and H for high confinement mode. The high confinement mode was immediately recognized as transformative. Doubling confinement time meant that a given plasma temperature and density could be achieved with roughly half the heating power, or equivalently, a much better fusion gain could be achieved in a device of given size. Modern tokamak designs, including ITER, are designed to operate in H mode, but H mode has a complication. At the edge of an H mode plasma, a sharp boundary forms, called the pedestal, where the plasma pressure drops steeply from its high core value to the lower edge value. This steep pressure gradient is unstable to a class of instabilities called edge-localized modes, abbreviated ELMs. ELMs are periodic, explosive events in which a chunk of the pedestal plasma is expelled outward, briefly doubling or tripling the heat load on the diverter. In a large reactor like ITER, the energy released in a single large ELM could be comparable to several megajoules deposited on the diverter surface in a few milliseconds, sufficient to melt tungsten and damage the plasma-facing components. Controlling or eliminating ELMs is one of the central plasma physics challenges of the ITER era. Several techniques have been developed and tested. Pellet injection, firing small pellets of frozen fuel into the edge of the plasma, can trigger many small ELMs rather than fewer large ones, distributing the energy more benignly. Applying small oscillating magnetic perturbations, called resonant magnetic perturbations, to the edge of the plasma can suppress ELMs entirely in some conditions. Alternative operational regimes that achieve H-mode-like confinement without ELMs have been discovered in recent years, including a regime called the I mode, discovered at Alcator C-mod at MIT, which has H-mode energy confinement, but L-mode particle confinement, reducing the pedestal instability. Which of these approaches will prove most practical in a reactor remains to be determined from ITER's experiments. The H-mode story illustrates a pattern that recurs throughout fusion research. Solutions to one problem create new problems. High confinement mode solves the confinement problem but creates the ELM problem. Tungsten plasma-facing components solve the material damage problem but create the tungsten impurity problem. If tungsten atoms enter the plasma core, they radiate so strongly that they quench the plasma temperature. Deuterium-tritium fusion solves the proton-proton reaction rate problem, but creates the neutron, tritium, and material activation problems. Each layer of solution reveals a new layer of challenge, and the cumulative engineering complexity of managing all of them simultaneously is what makes fusion reactor design so difficult. This stacking of challenges is not unique to fusion. The development of reliable turbofan jet engines, which power virtually all commercial aviation, involved similar cascading complexity. Early jet engines were simple in concept but failed frequently in practice because of materials problems, combustion instabilities, compressor surge, and dozens of other failure modes that only became apparent during operation. Solving each problem revealed the next one. It took decades of development, billions of dollars of investment, and the work of thousands of engineers before turbofan engines reached the extraordinary reliability that modern aviation depends on. Fusion faces a similar development trajectory, and the comparison suggests that the current phase of fusion development, in which engineering problems are being identified and systematically addressed, is the normal precursor to eventual commercial success, not evidence that the technology is fundamentally unworkable, The fuel for pessimism about fusion timelines is real. The fuel for optimism is also real. What is not warranted is certainty in either direction. The physics is settled. The engineering is not. The experimental programs underway will progressively reduce the uncertainty about what the engineering will cost and how long it will take. The appropriate response to this situation is sustained investment and honest communication about progress and setbacks. Exactly what the fusion community is increasingly, if imperfectly, providing. It is also worth noting what fusion is not competing against in the energy transition. Fusion is not competing against solar and wind for the next dollar of clean energy investment, because fusion is not deployable in the next few years, regardless of how much money is spent on it. Fusion is competing for the portion of the clean energy portfolio that addresses the problems that solar and wind cannot. Firm baseload, industrial heat, fuel production, geographical independence from renewable resources. Those are genuine needs in a fully decarbonized global energy system. And the investments being made in fusion today are investments in having a clean technology option available when those needs become acute, rather than being forced to rely on fossil fuels as backup for the clean energy system. The timeline for when those needs become urgent depends on how fast the renewable transition proceeds and how easily the remaining hard-to-abate sectors can be electrified. In the most optimistic scenarios, the need for fusion might be modest. A world that is 80 or 90% renewable might manage the remaining gaps with advanced storage and demand response. In more realistic scenarios, the need for firm, clean power and industrial heat will be significant, and the availability of commercially mature fusion technology in the 2040s or 50s would be enormously valuable. It is a technology in the right stage of development for the moment, in which we find ourselves advanced enough that we can see a path from current experiments to commercial deployment, not so advanced that the remaining work is trivial. The investment being made in it now will determine whether that path is walked quickly or slowly, whether fusion arrives as a solution in time to matter or as a vindication after the fact. That is a choice the current generation of policymakers, investors, scientists, and engineers is making, with consequences that will extend for decades. The sun does not care about our timelines. It will fuse hydrogen into helium at the same measured pace, whether or not we learn to do the same. But we care about our timelines. We have a planet to power without cooking it. We have civilizations that require energy at scales and reliabilities that cannot be compromised. We have an energy transition that is underway but incomplete, and that will determine the physical conditions under which all future generations live. In that context, the question of whether nuclear fusion can be made to work on a commercial timescale is not an academic curiosity. It is one of the most consequential technology questions of our time. The people working on it know this. They have known it for decades. They have kept working through the long stretches when progress seemed inadequate to the challenge. They are working now, with better tools and deeper understanding, and more company, both corporate and scientific, than at any previous point in the history of the effort. The probability of success is not 1, but it is higher than it has ever been. The distance between where we are and where we need to be has never been better mapped. The experiments that will tell us whether the map is accurate are already underway. The answers are coming. One of the more underappreciated aspects of fusion research is the role that plasma physics discoveries made in the pursuit of fusion have had on entirely separate fields. The study of hot, magnetized plasmas, developed specifically to understand fusion, has contributed to our understanding of space weather and the dynamics of the solar wind, the behavior of astrophysical jets emerging from black holes, the physics of lightning and plasma discharges in the atmosphere, and the behavior of matter under the extreme conditions found in the cores of giant planets. Plasma physics, developed as an engineering necessity for fusion, has become one of the foundational fields of modern physics. Applied to phenomena across 17 orders of magnitude in scale, from millimeter-scale laboratory discharges to million-kilometer-scale solar coronal structures. The reciprocal has also been true, understanding how the solar wind interacts with Earth's magnetic field, how magnetic reconnection, a process in which opposing magnetic field lines break and reform, releasing energy explosively, has informed the understanding of disruptive events in tokamak plasmas, where similar reconnection processes underlie the sudden loss of plasma confinement in a disruption. The interplay between astrophysical plasma physics and laboratory plasma physics has been scientifically productive for both communities. Solar flares, which occur when magnetic energy stored in the solar corona is suddenly released by reconnection events, produce bursts of X-rays, energetic particles, and coronal mass ejections that can damage satellites and power grids on Earth. Understanding the mechanisms of solar flares in detail requires understanding magnetic reconnection in a regime of plasma conditions. High temperature, low density, strong magnetic field that is different from the tokamak regime, but governed by the same underlying equations. Progress in understanding solar flares has informed the understanding of tokamak disruptions and vice versa. This cross-fertilization between space physics and fusion engineering is a genuine benefit of the deep investment in plasma physics that fusion research has motivated. Beyond plasma physics, fusion research has driven advances in superconducting magnet technology, cryogenic engineering, high-power microwave and radio frequency systems, vacuum science, remote handling robotics, neutron-resistant materials, and advanced diagnostic instrumentation. Many of these technologies have found applications well outside fusion. Superconducting magnets developed for fusion applications are now central to MRI machines, the medical imaging technology that has transformed diagnostics in hospitals around the world. The high-power gyrotrons used to heat fusion plasmas with millimeter-wave microwave radiation are finding applications in materials processing, plasma-assisted combustion, and medical sterilization. Neutron-resistant materials developed for fusion blankets inform the design of next-generation fission reactor components. The diagnostic techniques developed to measure plasma properties, Thomson scattering, charge exchange recombination spectroscopy, neutron tomography, are finding applications in combustion research, materials characterization, and medical physics. This technological spillover is part of the economic case for fusion research that is separate from and in addition to the direct value of fusion energy itself. Large scientific programs have historically generated technological benefits that exceed their costs, even when the primary scientific goal is not fully achieved. The Apollo program, which went far beyond its primary goal of lunar landing, produced advances in computing, materials science, telecommunications, and manufacturing that transformed multiple industries. The European Organization for Nuclear Research, CERN, developed the World Wide Web as an internal communication tool. It also advanced superconducting magnet technology, particle detector systems, and computational grid infrastructure, all of which have found broad applications outside particle physics. Fusion research, pursued at the current level for several more decades, regardless of whether commercial fusion power is achieved on any particular schedule, would likely generate similarly significant spin-off benefits. This is not an argument for pursuing fusion research inefficiently or without urgency. The climate challenge demands urgency in all clean energy development. But it is an argument that the investment in fusion is not simply a bet on a single commercial technology outcome, but a broad investment in the capability to understand and engineer plasma, one of the fundamental states of matter, with all the downstream benefits that understanding entails. The public perception of fusion research is complicated by the long history of optimistic predictions that were not borne out. When politicians and journalists report on fusion research today, they often lead with the historical cliché, fusion is always 30 years away, as a framing device that signals appropriate skepticism. This skepticism is, to some extent, earned, but it can also become a reflexive dismissal that ignores genuine recent progress. The December 2022 ignition result from the National Ignition Facility was a real milestone. The jet record in 2023 was a real achievement. The K-star plasma duration record was a genuine advance. The Commonwealth Fusion Systems magnet demonstration was a significant engineering milestone. Dismissing these results as just another fusion hype cycle requires ignoring specific technical achievements in favor of a historical narrative, which is a form of epistemic failure in the opposite direction from unqualified enthusiasm. The appropriate attitude toward fusion in 2026 is neither cheerleading nor dismissal. It is informed attention. The experiments underway will produce results within the next 5 to 10 years that will either confirm or refute the optimistic claims being made by private fusion companies and the public research programs. Those results, net energy gain demonstrated at engineering scale or not, tritium breeding demonstrated in test blankets or not, burning plasma physics understood and controlled or not, will provide an empirical basis for decisions about the next generation of fusion devices. At that point, the question of whether fusion will play a major role in the energy system will be substantially more answerable than it is today. That is where we are. Not at the beginning of the fusion story. The physics has been understood for decades, and the experimental programs are mature. Not at the end. Commercial plants are not operating, and may not be for another 20 years. We are somewhere in the middle, at a moment when the scientific foundation is solid. The engineering challenges are clearly identified. The tools available to address them are better than ever, and the resources being directed at the problem are larger than at any previous point in history. Whether the middle of the story ends with commercial success in time to matter for the energy transition, or with commercial success that arrives after the transition is substantially complete, or the outcome that has always been possible, but that looks increasingly unlikely, with continued intractability of the engineering challenges, will be determined by the work being done right now. Every second that passes, the sun fuses 600 million tons of hydrogen. It does not notice us. It does not care whether we solve the engineering problems we have set ourselves. It will keep burning long after the questions we are asking today have been answered one way or another. But we are the species that looked up at the sun and asked what it was made of and how it burned. And when the answer turned out to be nuclear fusion, we immediately started trying to do the same thing in a laboratory. We have been trying for 70 years. We are closer than we have ever been. The work continues. The physics is on our side. The rest is engineering. And engineering, given sufficient determination, tends to yield. The economic geography of fusion deployment, where the first commercial plants will be built, who will own them and who will benefit from their output, is a question that the physics community rarely addresses, but that will matter enormously for whether fusion fulfills its potential as a globally equitable energy technology or becomes another form of concentrated energy. Advantage. The high capital cost of first-generation fusion plants will likely mean they are built first in wealthy, industrialized nations with strong scientific and industrial bases: the United States, the United Kingdom, France, Japan, Korea, and China. This is the same pattern that characterized the early deployment of fission reactors in the 1950s and 60s, and of commercial solar manufacturing in the 2000s. The costs then fell as scale increased and manufacturing efficiency improved. Whether the cost reduction trajectory of fusion will be steep enough and fast enough to make fusion economically accessible to developing economies within a commercially relevant timescale is not clear from first principles. It will depend on the specific design choices made for commercial plants, the degree of international cooperation in technology transfer, and the regulatory frameworks that govern fusion plant construction in different countries. If fusion follows the trajectory of large fission reactors, expensive to build, complex to license, requiring a sophisticated industrial base, its geographic deployment may remain limited to wealthy nations for decades. If it follows the trajectory of wind turbines or solar panels, modular, manufacturable at scale, and readily transferable across manufacturing jurisdictions, it could diffuse globally much faster. The design choices being made by private fusion companies today will significantly influence this trajectory. Commonwealth Fusion Systems' emphasis on compact devices, reducing the plasma volume and hence the physical scale of the machine, is partly motivated by economics. Smaller machines are cheaper to build and easier to manufacture in series. Helion's approach of direct electrical generation, bypassing the steam turbine, eliminates a major capital cost component. General Fusion, a Canadian company backed by industrial investors, is pursuing a design in which liquid metal is spun into a vortex and then compressed by pistons to create momentary fusion conditions, an approach that, if it works, could potentially be manufactured at industrial scale without the precision machining requirements of large superconducting magnets. Each of these approaches makes different trade-offs between plasma performance and manufacturing simplicity, and the trade-offs that prove most favorable for commercial deployment are not yet clear. The question of intellectual property in fusion technology is also relevant. ITER's scientific results are shared among all member nations under the agreement governing the project. But the specific engineering designs of commercial fusion plants developed by private companies are proprietary, and those companies will seek to recoup their investment through licensing fees, royalties, and exclusive manufacturing agreements. This is a normal feature of technology commercialization, but it means that the benefits of fusion, if it is developed primarily by private companies, in wealthy nations, may not be as freely available to the rest of the world as the physics itself, international. Agreements on technology transfer for clean energy have a mixed track record. The Paris Agreement includes provisions for climate finance and technology transfer to developing nations, but implementation has been slow and the commitments made far short of what would be needed. If fusion becomes commercially available in the 2040s or beyond, the international framework for ensuring that its benefits reach energy-poor regions of the world will need to be negotiated long before deployment at scale. This is a policy challenge as important as any engineering challenge, and it deserves more attention from the fusion community than it currently receives. It is also worth noting the relationship between fusion and nuclear non-proliferation. One of the arguments sometimes made against fusion research is that the same knowledge and capabilities required to develop fusion energy could contribute to the spread of nuclear weapons. This argument is considerably weaker for fusion than for fission. The materials most relevant to weapons programs, highly enriched uranium and plutonium, are not produced in the main deuterium-tritium fusion reaction. Tritium is a component of thermonuclear weapons, but tritium is produced in fission reactors as well, and the connection between fusion power research and weapons-relevant tritium production is not straightforward. The international fusion research programs, conducted under the auspices of the International Atomic Energy Agency and through bilateral agreements, have historically maintained a clear separation between civilian fusion research and weapons programs. The spread of fusion power technology does not appear to pose the same proliferation risks as the spread of uranium enrichment or plutonium separation capabilities that are associated with fission. This does not mean fusion is without any security implications. A nation that achieves commercial fusion before others gains significant energy security advantages, independence from fossil fuel imports, reduced vulnerability to energy supply disruption, and potentially the ability to produce synthetic fuels at scale for transportation and industry. These advantages are not trivial. They may motivate accelerated national fusion programs in ways that could shift the balance of international cooperation versus competition that has characterized fusion research until now. As fusion approaches commercial viability, the strategic calculus of sharing technology versus maintaining competitive advantage will inevitably become more complex. These geopolitical dimensions are not arguments against pursuing fusion. They are aspects of its development that need to be thought through explicitly rather than assumed to resolve themselves. The history of every major energy technology, coal, oil, natural gas, fission, and renewables, is a history of both the physical technology and the geopolitical and economic frameworks through which that technology was deployed. Fusion will be no different. Getting the physics and engineering right is necessary but not sufficient. Getting the policy frameworks right for technology transfer, for nuclear safeguards, for regulatory harmonization, for climate finance will be equally important to whether fusion delivers on its potential as a genuinely transformative and globally accessible energy source. The good news is that none of these policy challenges are new in kind. They are versions of challenges that have been addressed before, imperfectly, in the governance of earlier energy technologies. The international community has experience with technology transfer agreements, with nuclear safeguards under the Non-Proliferation Treaty, with multilateral scientific cooperation under ITER's governance model, and with climate finance under the Paris Agreement. None of these frameworks are perfect, and fusion will likely require new frameworks tailored to its specific characteristics. But building on existing experience, rather than starting from scratch, is a significant advantage. The next major milestone in fusion research is likely to be achieved within the next few years. Whether it is ITER achieving first plasma operations, a private company demonstrating net energy gain at engineering scale, the successful demonstration of tritium breeding in a test blanket, or some other result that advances the field in a way that is currently unanticipated, there will be a moment in the near future when the trajectory of fusion's commercial development becomes considerably clearer than it is today. That moment will be recognized as significant in retrospect, whether it confirms the optimism of the current moment or reveals that the challenges are even harder than they appear from where we stand now. The people watching for that moment, the physicists and engineers running the experiments, the investors monitoring progress in portfolio companies, the policymakers shaping research budgets, the scientists communicating with the public about what fusion can and cannot deliver, are all participants in the working out of one of the most consequential scientific and engineering questions of the 21st century. The outcome matters, the work continues, and every second, At the center of the sun, the process we are trying to learn to harness keeps operating, patient and indifferent to our efforts, at the scale that only a star can achieve.